Okay, the third and final style of volume question that you could expect to see on your AP Calc 2 exam is known cross-sections. And these are kind of tough to visualize. People often grow frustrated because it's hard to see what's going on. With shells and washers, these are our two formulas, and they are based on just the geometry of what we're summing up. In a shell, we are doing a bunch of shells. You can imagine them kind of like nested dolls, or, it's like a bunch of different sized little cans, maybe. But they sit within each other, and they basically, if you were to unfold this thing, you get a rectangular solid, and its length is the circumference of a circle. So the 2 pi and the radius give you the length, or the distance around the circular portion. The height gives you how tall the can is, and then the dx provides for the thickness. So that's how I remember 2 pi radius times height. You need to have these, in my opinion, when you hear shells, you need to think 2 pi radius height. And then all the details, if it's dx problem, if you have a vertical rectangle, then everything needs to be in terms of x, the radius and the height and all that. And you can work out those details on the spot, but if you don't remember 2 pi radius height, then you're done before you even start. A washer takes that same rectangle and it spins it perpendicular to the way it's arranged. So it looks sort of like this. And this is just a more complicated version of the disk method. I don't focus on the disk method because way more often on the AP exam, there's going to be a hole in the middle. There's going to be a big radius and a small radius. So this is based on basically a little tiny cylinder. It's the area of the circle with a little bit of thickness. So basically what we're doing here is we're taking pi times the big radius squared with thickness, and we're subtracting pi times the little radius squared with thickness. But instead of doing two separate integrals, we put big R squared minus little r squared in the same integral and just integrate once. Very common mistake is to do this, subtract them and then square. Very common, but very wrong. So don't do that. All right, so that brings us to this topic. We're going to talk about known cross sections. So basically all this means is we're given an area, a two-dimensional area in the xy plane. The volume comes up out of the xy plane, and no matter where you slice it, you get a certain geometric shape. A lot of times it's a semicircle. It could be a square or a rectangle or a certain kind of triangle. It's kind of hard to visualize, so I'm going to try to draw one in 3D here. Let's say we take our x-axis this way, but we take our y-axis, kind of imagine this as the floor, and then our z-axis, we're not really in 3 variables, so it's not really a z, but I just wanted to give, the idea that this is the floor, and whatever, the shape that's in the xy plane, it could be anything. And then the shape comes up out of the floor, and it's kind of hard to draw without, shading. But if you were to slice this shape at any place, you would get maybe a semicircle in this case. Try to start this over here. It's not a great picture. Let me start with a circle. If I had a circle in the xy plane, and my cross sections were all semicircles, and that would make like a hemisphere. So that's kind of hard to, you kind of get the idea. No matter what, if I were to take a knife and slice this thing, I'm going to get a semicircle every time. So I slice it down here, I get a small semicircle. I slice it towards the middle, and I get a bigger semicircle. The one that's right in the middle is the biggest semicircle. But no matter what, when I slice it, I get the same cross-section, which is why this is called known cross-section. Now, it's hard to visualize, it's kind of hard to explain, but it's easy to work. So let's start with an example. All right, so I searched through some old AP problems, and I'm going to do this one. I like this one because not only does it give us in Part B a cross-section question, but it makes us do it perpendicular to the y-axis, which adds a little bit of level of difficulty, but not too bad. So we have our two functions. We have the square root of x here in red, right? We have 6 minus x, which is just a straight line, slope -1. It would cross at +6 if we extended it upward. And in Part B, the region R is the base of the solid. Okay, so that's like the floor. The solid is coming out of the picture at you, and no matter what, if you were to slice this shape for y between 0 and 2, okay, the cross section perpendicular to the y-axis. So you take a knife and you cut through this solid, which is hard to, sometimes hard to visualize. Like I said, it's coming up at you, but you cut it, and you get whose height is 2y. Now, that's really hard to visualize what it might look like, but the good thing is it doesn't really matter. We get a rectangle whose base is in R and whose height is 2y. So let's say I'm here at 1. Let me move my blue line up a little bit. Actually, better yet, I've already used blue for that function, so let's use a green line. If I were to cut this thing, this shape, cut down through it, whatever my height is, basically whatever my y value is, which here it's 1 because I'm at a height of 1, that's the height of the rectangle. So down here, I have a very short rectangle that's the longest, and up here I have a tall rectangle that's 2 units high and just very narrow. So you can kind of imagine it going up to a point up at the top there, and then a big flat, a smaller and smaller rectangle that kind of disappears down to nothing down here at the bottom. That one's kind of, like I said, it's tough to visualize, but here's the good part. We have our two memory devices for shells. Shells, 2 pi radius height, washers, pi on the outside, big R squared minus little r squared. The good news about these cross-section ones, it's the easiest of all the three. The cross-sectional volume is equal to the integral of the area, dx. Now, the area dx is just an area with thickness, which is really all we did back here. The area on these other two, 2 pi radius height, that's the area of the rectangle that's been curled up into a shell, and dx is the thickness. Pi r squared, or big R minus little r if you have a washer, that's the area, and dx is the thickness. So we really haven't changed that up. It's just that we don't have a guaranteed specific shape every time. Those other two are based on circles because we are rotating an area around, and that's what happens when you rotate something. You create circles, or a system of interconnected shells, or a system of washers that sit right next to each other. This is, you have to adapt to whatever the question is, but it's usually a pretty easy area. We have a rectangle whose base is in R and whose height is 2y. All right? So just start with the expression here, the integral from a to b of the area, and then I use dx because it's almost always dx. Actually, in this case, it's going to be dy, because think about this. It's making us slice this thing perpendicular to the y-axis, so everything's in terms of y. So let's just go ahead and fill out the easy parts. The volume we're looking for is the integral from y value. As we move from bottom to top, we have y equals 0 to y equals 2. And you're fine with just 0 and 2, but for emphasis, I'm going to say y equals. Now, I need to integrate a bunch of little rectangles with thickness. I'm going to add up the volumes of a bunch of rectangles with thickness. A rectangle is just length times width. So I'm going to fill that in on this step, and then we'll get to the specifics. Now, the thickness is just the dy. So all I need right now is an expression for the length of each rectangle in terms of y and the width of each rectangle in terms of y. So back to the picture. Try to add in some 3D here. So this is the slice. Comes up out of the picture at you. There's the thickness. That might show you something, who knows. Up here we've got the little bit taller ones, because this one would need to be 2 units. almost 2 units because it's 2 units tall. And down here, I've got the long, thin rectangle. And then they kind of, I'm going to ruin my picture by trying to add too much to it. It kind of swoops down to make a, I don't know what that looks like. It's in a really awkward shape. Let's forget about all that and get back to the length times width. All right, so each rectangle, the length, or this dimension, is just the difference in the two graphs. So it's the blue function minus the red function. Because remember, when you go dy, it's kind of like the right is the top and the left is the bottom, or the right are the bigger numbers, the left is the smaller numbers. I need to get everything in terms of y. So my blue function, y equals 6 minus x, I need to solve that for x and say x equals 6 minus y. Just rearrange, move the x over and move the y over. My red function, y equals the square root of x, is y squared equals x. All right? So that way, I can express my length and my width using those, because everything has to be in terms of y. All right, so the height of the rectangle, I guess they're using height instead of width. They're interchangeable. You just have 3 dimensions in a rectangle. All right, so one dimension in my rectangle is the difference in the two functions. Well, that's 6 minus y squared. That is the dimension of the rectangle that goes across your paper. All right, I guess they're calling this the width. The height of this rectangle coming up out of the board at you is always 2y. So for me, maybe I should call that, it doesn't matter. This is kind of misleading because of the 2 different terms. But this rectangle is 1 dimension, the difference in the graphs. The other dimension was given to be 2y. Sometimes they'll say that it's the, every rectangle has a height of 3. Sometimes it'll be a semicircle or whatever. But those are the 2 dimensions of our rectangle. And then the dy gives it its little bit of thickness in the y direction. All right, so that's the integral that we need to solve. And actually, lucky for us, it says we have to write but do not evaluate the integral. So if this were a calculator question, we could type it in our calculator and get the answer. If it were a non-calculator, they might ask us to solve it, but they didn't ask us to solve it. So all we need to do is just confirm. I'm going to go to the answer. We have 6 minus y squared times 2y from 0 to 2. And here's the answer. 6 minus y squared times 2y from 0 to 2. So it worked out according to their answer as well. So this is kind of one, it's a little bit of a struggle to try to make this. It's hard to explain. It's hard to visualize and try to draw. But just remember this. Integrate the area and give it thickness. So this is our third thing we're going to remember. All right, it's very likely you'll get a question that you have to do 2 or 3 or maybe all 3 of these styles of volumes. And knowing those will get you started. All right, and then we can practice the details after that. All right, so 3 out of 3 volume videos done. See you in class. Young out.